taking the case on behalf of the fourth dimension. Hypothesis proposing the existence of a quantum-type process linked to gravity, which produces alteration of matter, in a framework of 4 spatial dimensions plus time. Gravity, beyond the standard model of relativity. Science versus science fiction. Conceivable proposal. In an inconceivable world.
Most of the people do not believe in the existence of a fourth spatial dimension. Or we could say, that only people keen to paranormal phenomena are willing to seriously consider this possibility. Encounters with aliens, traveling to the past, or the fourth dimension, are topics that belong to science fiction books. In order to back any theory, science requires reliable evidences, strong arguments and testable results. The consensus among the scientific community is that a fourth spatial dimension is a speculative idea. Although, there are alternative theories, which include additional dimensions. In 1919, Kaluza proposed a model with an extra dimension as a possible way to combine gravitation and electromagnetism. This additional dimension would be compactified, being the reason for us to be unaware of it. Since Kaluza's proposal, there have been many new theories that postulate additional dimensions. String theory is the most famous, with a total of 11 dimensions. Also in this case, the special nature of the extra dimensions makes it very difficult for us to detect them. This theory is supported by a considerable group of respected scientists. But it is also criticized by some orthodox scientists, who consider that it still lacks sufficient experimental evidence. Other theories, such as general relativity, have allowed us to make very accurate calculations and predictions, successfully passing many rigorous tests. It has to be said that it took decades for science to experimentally test some of the predictions, which required very important technological advances to do so. For example, the detection of gravitational waves was only possible 100 years after the publication of General Relativity. So maybe the string theory is too sophisticated in relation to the current technological level. Who knows if, for instance, in the future, the postulated additional dimensions are detected. It should be conceded that many scientists do take seriously, at least hypothetically, the existence of additional dimensions, even though there are no experimental evidence to prove that they are a physical reality. Or perhaps, it should be said that we are not aware of having detected them. Because the argument that will be defended here is that there are many indications pointing towards the existence of an additional dimension. And some prominent experiments realized during the last century, with the aim of proving the curvature of space-time, are also backing the existence of a fourth spatial dimension. It just requires a Copernican shift to get an alternative interpretation of the available data, which could help us better understand the phenomenon of gravity. But, first of all, it has to be explained the characteristics that the supposed fourth dimension would have. The first feature to keep in mind is that the trajectory followed by a body has additional components beyond the up, down, left, right, front and back. So that, when I go from my office to the boss one, I will walk 5 steps on my front, 12 stairs up, 20 steps on the right, plus an additional value on the fourth dimension. Another feature to take into account is that the volume of a body will be the result of the combination of four components: length, width, height, plus a fourth one. Besides, it will be required 5 dimensions, 4 spatial ones, plus time, in order to assign univocally physical values of the body, such as its mass. If the dimension is not compactified, then we should detect all these features. Traveling through 4 dimensions, undefined values simply using 3 spatial plus time coordinates. These are issues that even a flat Earth believer would be reluctant to deal with. At first sight, defending the idea that a fourth dimension is not just a science fiction issue seems to be a lost case. Nonetheless, if we thoroughly analyze all the peculiar characteristics of the universe in which we live, that would be a logical conclusion, and following will be discussed the arguments to come to this idea. To begin with, physical reality does not behave in the way that we are used to intuitively assume in our daily lives. We have to take into account quantum mechanics and relativity. In publishing the theory of special relativity, Einstein introduced the concepts of time dilation and length contraction within the context of relativity, leaving aside the idea of an absolute value of time. The passage of time slows down in relation to hours for objects with velocity relative to us. But to get a significant effect, the velocity must be close to the speed of light. That is why time dilation and length contraction pass unnoticed to us in our daily lives. Concerning scenarios of special relativity, the values corresponding to the length, or the passage of time, depend on the frame of reference taken. For example, the Earth moves with relativistic velocity in relation to the International Space Station. Therefore, in the direction of velocity, if 3 steps are exactly 6 feet for us, it would be slightly different from the point of view of someone located at the International Space Station. We must also take into account the effect produced by gravitational fields. The theory of general relativity, developed by Einstein, defines gravity as the curvature of the space-time framework, which implies that space and time values differ for people located in regions of a gravitational field with different space-time curvature. The effect produced by the Earth is greater at its surface than at the International Space Station. The previous example, defining the trajectory and location via steps, although intuitive, is not very useful when making calculations concerning gravity. Physicists define an elementary path using a line element. General relativity allows to mathematically calculate the metric, which is used to define the trajectory that a test particle would follow in the curved space-time. The line element is composed by the combination of 4 components, the 3 spatial dimensions, plus a 4th component, which is linked to time. This combination configures the space-time framework. It is well worth noticing that the dimension linked to time is embedded into the space-time framework via the transformation into a space value. An astronaut traveling from the Earth to the International Space Station would not perceive any significant alteration inside the spaceship, but when contrasting the values of space and time with other references, then he observes the predicted discrepancies. Besides, the trajectory of the spaceship takes place in a curved space-time. Based on this peculiar phenomenon, we can conclude that we should not simply rely on our primitive intuitive perception if we want to reach a fully comprehension of the physical reality that surrounds us. it is required to adopt a higher mental approach, gathering all available information, to deduce what is happening. So far, it is fair to take into account, to support the case of a fourth dimension, the following arguments. First, the fact that we do not directly perceive an additional dimension, does not necessarily mean that it does not exist. Obviously, it does not prove its existence either, it just opens the door to a new plausible approach, and this idea will be developed later. Secondly, it is not enough the assignation of 3 dimensions, in order to define the trajectory of a body. It can be argued that the fourth dimension, which is embedded with the other 3, to configure the space-time framework, corresponds to time. Although, we should say better, that it is linked to time, and we must also bear in mind, that the component embedded in the space-time framework, is the value of time multiplied by the constant value of the speed of light, giving as result, a space-like magnitude. It is true, that this component allows us to calculate, the alteration of the time produced by the presence of gravitational fields, but this circumstance, does not demonstrate beyond a reasonable doubt, that time is the fourth component, of what has been called, space-time framework. There are other logical explanations for that behavior. Next, it will be set forth the basic principles of an hypothetical quantum-type process linked to gravity, that produces the alteration of matter, within a framework of 4 spatial dimensions plus time, which would be responsible for all the peculiar characteristics previously described. In summary, what has been argued so far, is that the theory of general relativity, is based on a mathematical model, that establishes very peculiar rules. Analyzing them with the different criterion, we can make an alternative interpretation. Proposing the existence of an additional dimension, or changing any criteria concerning general relativity are lost cases, a priori. That is the reason for this long introduction and the need to focus on some outstanding features, which acquire a new physical meaning, when we take a different approach. It is time to introduce the proposed hypothesis. It will be schematically explained how the process works. Previously, it has been stated, that it is a quantum-type process. If general relativity, is the theory, that best fits the observations concerning gravity, quantum mechanics establishes mathematical models for the other fundamental forces of nature, such as electromagnetism. Quantum mechanics is characterized by the assignment of probability factors to events. For example, we do not know for sure, if an electron is located in a particular region of space at a given time. Instead, what we know, is the probability of finding the electron there. The proposed process produces an alteration of the expected probability, and in doing so, not only matter is altered, but also space-time is distorted. In this way, the probability linked to a particle, for example, an electron, is represented schematically. The bigger the green circle, the higher the probability of finding the electron in that elementary region of space. The interactions caused by the presence of gravitational fields, produce alteration of matter and space-time, changing the physical state of particles. Naming, alpha state, to the initial state, represented by a green circle, and beta state to the altered one, red circle. The interactions taking place, reduce the probability of the particle in the alpha state, while increasing the probability of being in the beta state. Space-time, is curved by the gravitational phenomena, with an interrelation between the spatial coordinates, and the time coordinate. The hypothesis postulates, that the 4-dimensional framework, configured by the 3 spatial dimensions, plus the 4th, which is linked to time. It is really, a true genuine 4-spatial dimensional framework. Furthermore, the process that produces the alteration of matter, is what produces the alteration of space. Matter in the alpha state, is linked to the three conventional dimensions. Meanwhile, matter, in the beta state, is linked to the fourth. And that is the reason for the interrelation among the four dimensions, because the last one is generated at the expense of the other three. The Einstein's field equations provide information about the alteration of matter for any given coordinate. That is to say, they do not only define the trajectory that a body follows, but also correspond to the deformation that is suffering in a four-spatial plus the time-dimensional framework, and the deformation of everything that configures the spacetime is what defines the trajectory of the body in this five-dimensional framework. The interactions, due to the proposed process, reduce the probability of a particle in the alpha state, which is linked to the three conventional dimensions. If this happens with everything located within that region of space, and assuming that what is inside is responsible of shaping the space, then the space inside that region, corresponding to the three conventional dimensions, is contracting. Noting in this way that a relationship between matter and space has been established. Matter and everything inside a region of space shapes the space. If we consider a gravitational field, like the one corresponding to the Earth, the closer to the source, the stronger the effect. The closer an object is to the surface of the Earth, the greater the amount of mass in the beta state linked to the object. And there is a correspondence between the alteration of matter and the curvature established by the Einstein's field equations. Until now, from a practical point of view, the proposal has only changed a criterion, when it has been postulated, a four-spatial dimensional framework. But what about the time dimension? Considering a distortion of the time dimension, in the same proportion as the distortion of the fourth spatial one, then the value of the mass in the alpha state and its fundamental features are restored. But now in a curved spacetime, which has the curvature defined by general relativity, with some nuances. To begin with, added to the initial mass, called here matter in the alpha state, there is also matter in beta state, which has an extremely small value for the gravitational field of the Earth. It would be less than 1 grain for an object of 1 trillion tons. But the proportion would be higher if the object is located in a region where the gravitational field is stronger, for example, close to the Sun, and would be a lot much higher if located close to a black hole. Another issue to keep in mind is that the value of the mass depends on the reference taken. So far, it is proposed that gravitational fields disturb the probability associated with an event, producing its corresponding effect on the curvature of the four-spatial dimensional framework, represented here by 4 arbitrary coordinates. And the distortion of time is towards the initial value of probability, called alpha state, but now, there is an additional component of probability, the beta state. What happens with the probabilities can be extrapolated to the mass of objects. From the initial mass, it is obtained the same mass value in the alpha state, plus an additional amount in the beta state. Having established a relation between the alteration that takes place and the curvature of space-time, where the change for any coordinate will depend on this alteration. That is to say, the proposed process produces the physical effect, from which the metric emanates. For example, has its corresponding effect in the change associated with the Schwarzschild radial coordinate, where the closer to the source, the greater the alteration. The hypothesis proposes that gravity produces alteration of matter and space-time, establishing a relationship between the alteration taking place and the curvature of space-time. Another remarkable characteristic of the process is the increase in the value of the resulting matter, and that value depends on the reference taken. All of them are very peculiar features, and we could get to the conclusion that the defined process is not part of nature, because the universe in which we live does not show such bizarre behavior. Or maybe it really does. Regarding bodies with velocity relative to a reference, Einstein introduced the concept of relativistic mass, whose value depends on the frame of reference taken. And, when approaching special relativity, from the point of view of the proposal, the interpretation of this physical phenomenon is that, when kinetic energy is applied to a body, then, the process is boosted. It should be taken into account that a pure special relativity scenario, in the absence of gravitational fields, is an idealized situation, since that would require an infinite distance from the sources of gravity. Therefore, and assuming that when a body gains kinetic energy, the process is reinforced. This implies that matter is being altered further, with its corresponding spacetime distortion. Applying the model established by the proposal to the special relativity scenario, on the basis that the physical effect of the kinetic energy corresponds to a boost in the process, which increases the amount of mass in the beta state. There is also an interrelation between the alteration of matter and the distortion of space. The Lorentz factor is determined by the process. This has important implications, because the factor would be a consequence of the interactions taking place. Once again, following the same pattern as in general relativity scenario, the greater the alteration into the beta state, the higher the distortion of time. Being the value of the energy linked to the beta state, the same as the value of the kinetic energy, we might come to the conclusion that when an object is increasing its kinetic energy, in fact, what is happening is that it is gaining mass in the beta state, whose corresponding energy is what we call kinetic energy. The addition of mass in the beta state to the mass in the alpha state is what Einstein defined as the relativistic mass. It is schematically represented, the alteration of matter, and its relationship with the space-time. The scheme includes the additional spatial dimension, extending the standard dimensional framework. It must be taken into account that a Minkowski space is required to represent geometrically the standard space-time framework for special relativity scenarios, and the Riemann space would be required for general relativity ones. Following the proposed model, and applying it to special relativity, the very same mathematical results are obtained, as with the standard model of relativity. It has been changed the criterion, in the physical interpretation. But, the model, including its extremely peculiar characteristics, fits the experimental observations. These features correspond to the ones previously defined, which would be the expected, in a universe with 4 spatial dimensions. The proposal implies that the value of the mass depends on the reference taken, changing with velocity in the case of special relativity, and will depend on the curvature produced by the gravitational field when affected by them. That is to say, different velocities in a negligible gravitational field environment have associated variable values of mass, and different locations in a gravitational field, with different curvatures, but forced in a static state, also have associated variable mass values. Simultaneity of velocity and the presence of gravitational fields form a combination of both states. Therefore, the movement of a body, in what we call the space-time framework, is in fact, the movement in a 4-spatial dimensional framework, which is curved by gravity. The trajectory is schematically represented. It can be calculated using general relativity, but should include the additional effects due to the proposed process, where we have to add the dimension of time, which runs inexorably. And the alteration of time is the same as the corresponding to the 4th spatial dimension. So it can mislead us, coming to the conclusion that the body is moving in a 4 space-time dimensions framework, when in fact is moving in a 4 spatial one, plus time. So that, the standard model of general relativity is overlapping the 4th spatial dimension with time. In this way, what the astronaut traveling from the International Space Station back to the Earth would consider, from his point of view, as just a straightforward movement, when he walks 3 steps ahead, it is in fact realized including an extra dimension. But his continuous adaptation to the new environment creates the illusion of movement in a 3-spatial dimensional framework, when in fact, he is traveling through a framework with 4 components. And the curvature of space is a consequence of that physical reality. What we perceive as an obvious fact that is not subject to discussion, it becomes a relative situation when we add an additional dimension. What we consider as a well-defined mass value for an object, it is an undefined value, if we do not add an extra component of information. The mass of a body has a different value depending on the curvature of space, and the value will be different for people located in regions of space with different curvatures, which is an extension of the concept of relativity. When Gulliver traveled to the wonderful island of Lilliput, he faced the physical reality of a tiny, but fully functional world, with people enjoying lives not too much different from ours. But what would happen if during his journey towards the island of Lilliput, he suffers a transformation, being adapted to the environment, so that, when he arrives to the island, he becomes a tiny person, being exposed to the same phenomenon, which affects the island? He would not perceive the change directly. Similarly, we are continuously adapting to the physical state of our environment, and we do not directly perceive the alteration of length, time or mass. But indirectly we can deduce what is going on, resulting in the alteration of space, time and matter. Summarizing all the above, gravitational fields produce the alteration of bodies in a 4-spatial plus time-dimensional framework. The alteration that takes place on any coordinate is collected by the Einstein's field equations, where the distortion of the space-time framework is replicating the alteration of matter, and everything that configures the space-time. But now we have to take into account an extra dimension, so that physical values such as the mass of a body are not sufficiently defined using 3 spatial dimensions plus time. We have to specify the curvature that is affecting it, in order to know its configuration in the extra dimension. Besides, the mass value will depend on the reference taken. In other words, relativity is nothing other than the physical consequence of the effects produced by an extra dimension. In this way, when analyzing special relativity, from the point of view of the proposal, it is assumed that the interactions taking place, which produce the alteration of the matter and the configuration of the space-time framework, are further being boosted when kinetic energy is applied. So that, if we apply energy to the laboratory of twin B, in order to get it moving with velocity close to the speed of light relative to twin A, where each one performs his own experiments. For example, the probability linked to the decay of a radioactive material after a set period of time. Each brother has his own time controller. It might be an atomic clock, or any other like an hourglass. It's just a way of representing the rate of time that passes. Twin A will observe that time in his brother's laboratory passes more slowly. Therefore, the results of the laboratory B, to reach the same values of probability, will take longer, from the point of view of twin A, than those carried out in his own laboratory. Or we could say, that the alteration of the probabilities, is the cause of the dilation of time. But what about the observations carried out by twin B, in his own laboratory? The change in the interactions with respect to the physical state, when he was at rest with his brother, produces the alteration of the radioactive material. But this very same alteration is occurring in the atomic clock, or in any other time controller, that he uses to count the passage of time. So that, from his point of view, just analyzing what is happening inside his laboratory, nothing has changed, either at rest, or with velocity relative to a previous physical state, which configures a different frame of reference. This phenomenon of dependence on the reference taken, also applies to spatial dimensions. there is length contraction in the direction of velocity, and the measurement patterns change in relation to a particular frame of reference, since the physical state is altered due to different interaction situations. Twin A will observe length contraction in laboratory B. But twin B is not aware of any changes in his own laboratory. It is only when there is exchange of information, or interactions with other frames of references, that he realizes the disagreement between both physical states. Similarly, when considering mass of objects, there is a relativistic mass, whose value depends on the frame of reference taken. It has to be noted, the interrelational established by the proposal, between space-time and matter. While from the reference frame of twin A, there is alteration of space-time and matter in the laboratory B. His brother does not perceive any alteration in his own frame of reference. The adaptation to the new physical state would be the reason not to perceive directly neither the fourth spatial dimension, nor the additional mass. But we would indirectly detect its effects by contrasting our frame of reference with others. Concerning gravitational scenarios, a person in free fall would not perceive any significant change in matter and space-time. In a local range around him, the shorter the range, and the weaker the gravitational field, the smaller it is the change. So, he is not aware of the fourth spatial dimension or of the additional matter. But when you see the whole picture, then you realize that the space-time is curved in relation to other references. In this way, we only detect indirectly the effects of the altered matter in a four-spatial dimensional framework. For example, we can see light bending when passing close to a massive body, like the Sun. As previously stated, this approach does not modify the expected results concerning special relativity scenarios. Discrepancies arise when considering the effects of gravitational fields. But it is required very strong ones in order to obtain significant discrepancies. In a free-fall scenario, for the process to take place, it is required the conversion of a partial quantity of energy linked to velocity into energy linked to the mass of the object, acting as a counter-effect on the distortion of any coordinate. This counter-effect of energy opposed to the curvature of space-time, established by the standard model of relativity, is extremely small in relation to the effect produced by the curvature for gravitational fields such as Earth's, but the proportion increases the stronger the gravity. When comparing the effect produced by the process with the free-fall scenario of the standard model, we would conclude that gravity increases the energy required to confine a particle within a region of space. A fundamental feature of quantum mechanics is the requirement of energy in order to confine a particle within a region of space. The energy required increases, the smaller the region. General relativity implies that when there is matter inside a region of space, the particle is affected by space-time curvature, but not a conventional force effect is taking place. The effect due to the proposed process implies that complementary to the space-time curvature, the presence of matter further increases the energy required to confine the particle. That discrepancies with respect to the standard model are greater the closer to the source of the gravitational field, and the stronger it is. The graph represents free-fall velocities. Black lines correspond to the standard model, red ones to the proposal. The closer to the left side, the closer to the surface of the sphere, source of the gravitational field. The bigger the factor linked to the sphere, the stronger is the gravitational field generated. If the hypothesis is correct, it would have very important implications in cosmology, and should be taken into account when considering phenomena related to dark energy and dark matter. It would also have transcendent effects on black hole events. The proposed approach could give a new insight into gravity. All the forces of nature, but gravity, have mathematical models based on quantum mechanics. As previously stated, quantum theory establishes the requirement of energy if we want to confine a particle within a region of space, increasing the energy required, the smaller the region, reaching an infinite value when it has a zero size. But what happens when there is matter inside a region of space, and we try to confine the particle within this region? Let's suppose a homogeneous and uniform distribution of material within a sphere, and a particle on the surface. As we compress this sphere, the energy required to further advance this action increases substantially. Based on the behavior of nature, concerning quantum mechanics, we should expect the amount of energy required to confine the particle within the object, when this reaches zero size, to be infinite. But we have to take into account the effects due to the gravitational field generated by matter, and the mathematical model we use for gravity is not quantum mechanics, but general relativity, which defines the effects of gravity as the curvature of the space-time framework, and this curvature increases, the stronger is the gravitational field. In this way, when we reduce the size of the object, we increase the effects of gravity on its surroundings, with its corresponding spacetime distortion. What general relativity predicts, when the object reaches the size corresponding to the Schwarzschild radius, is that a black hole event is generated. What happens next is still subject to discussion, but the mainstream considers that the evolution of this event is a collapse towards a singularity, and nothing can prevent the particle located on the surface from falling into the black hole event. This hypothetical physical system, where energy is boosting the strength of the gravitational field, shows a close relationship between gravity, matter, energy and space-time. Initially, when we begin to compress the sphere, the gravitational effects are insignificant, but they increase progressively as the radius is reduced. The applied energy is continuously overcoming the internal forces of the sphere, producing deformation of the body. In our daily life, intuitively, we assume that energy deforms the spatial configuration of bodies, or alters the path they follow, within a framework of 3 spatial dimensions plus time. But when we add an extra dimension, then the evolution of the sphere and the particle takes place within a framework of 4 spatial dimensions plus time. The standard model of relativity establishes that when the black hole has been generated, an infinite amount of energy is required to prevent the particle from falling into the sphere. But taking into account the proposed process, the deformation of the particle in 4 spatial dimensions, hypothetically reaching the event horizon, would have linked an infinite amount of energy, and that energy would be obtained at the expense of its velocity, creating the effect of an infinite amount of energy opposite to the free fall of the particle. In this way, the state of the particle in the event horizon requires an infinite amount of energy, similar to the special relativity scenario, which requires an infinite amount of energy to get the physical state corresponding to the speed of light. The previous example should also take into account that the value of matter will depend on the reference taken. Thus, the value of the mass corresponding to each elementary region of the sphere with respect to the particle will depend on the space-time curvature of each elementary region of the sphere with respect to the curvature of the particle. This effect of dependence on the reference taken is negligible, considering gravitational fields such as the one generated by the Sun, where there are small variations in value. But when the gravitational field is much stronger, then it would have a very significant effect. For example, the value of the mass located in the center of the galaxies would be greater for the stars located in the outer region of the galaxy, being greater the longer the distance, since it is increasing the value of the curvature of the mass located in the center with respect to the curvature of the star considered. And indeed, nature shows an anomalous behavior, where the outer stars have higher orbital velocities than the expected by the standard model of relativity. In order to fit the observations, it has been required to add the hypothetical existence of dark matter, which has not yet been identified. The additional effects produced by the proposed process should also be taken into account when analyzing phenomena related to the Big Bang or the expansion of the universe. In the Big Bang event, the curvature of the framework configured by 4 spatial dimensions plus time would have associated a huge amount of energy linked to the beta state. During the period of inflation, the energy released would promote a rapid expansion of the universe. In an expansion scenario, the reverse process takes place with its corresponding alterations in mass, energy and space-time. So, the proposed process draws even a much more complex physical reality than that assumed by the standard model of relativity, especially in relation to the mass of the bodies, which will depend on the curvature, and this one is due to the resulting cross-interactions generated by the gravitational fields being boosted by energy momentum, everything embedded in a framework of 4 spatial dimensions plus the time dimension. A quantum-type process has been proposed, which changes the physical state of matter and shapes space-time, producing effects not taken into account by the standard model. Discrepancies are insignificant for gravitational fields such as the Earth's, but they must be taken into account for stronger ones, which would have outstanding implications in cosmology. If nature behaves as proposed, it should show very peculiar characteristics, and that is the case of the special relativity scenario. Can it all be a coincidence?